Desai, and this is my Physics 212 Lab 4 for bar magnets. For the introduction, the purpose of this lab was to examine how the magnetic field of a bar magnet changes with distance, and our goal is to compare the observed magnetic field to the predicted values for both on-axis positions. To make these predictions, we used WebVPython for both visualization and calculation. So the fundamental physics principles, we use the Biot-Savart law, which describes the magnetic field generated by electric current, and then the magnetic field of a dipole, which is the field produced by a magnetic dipole, such as a small current loop or a bar magnet, and we use a bar magnet in this lab. And then the distance dependence formula, which is the distance dependence formula for a magnetic field, describes how the field strength decreases with distance. And then for our assumptions, we said no other magnetic field except bar magnet and the Earth. Bar magnet acts as a magnetic dipole. The magnetometer is perfectly aligned with Earth's north-south axis. The magnetic field falls off as distance increases, and we know where the magnetometer chip is on the phone. So for our results, we got n is equal to negative 3.229. And then you could see we got ln k, or the natural log of k is equal to negative 14.151, which we could then use to find that k is equal to 7.15 times 10 to the negative 7th. And then the magnetic dipole moment we got was 3.575. So the initial conditions, we had the bar magnet, smartphone with a magnetometer, meter stick, and tape. As you can see in this diagram, we mark the chip of the phone using this tape, and then we align the phone in various ways to get our measurements. And then here was the on-axis data table here. As you can see, we have our line right here with the equation y equals negative 3.2292x minus 14.151. And this makes sense. It's supposed to be a inverse relationship line. So yeah. And then calculations was some short calculations to help get mu, which is 3.575, with a magnetic dipole moment. And then for the off-axis experiment, you can see all of our data here. dperp, the average of that was 0.45. And then, yeah. So here's our computational model. Here's the first part of our code. We can see our magnetic field equation over here. And then we have all of our arrows using axis 1, axis 2, and such. And then computation model continued. We put in our average d perpendicular here, and then we got d is equal to 0.636396, and then b at 45 degree at distance d. We can see this vector is what we got. And then possible sources of error in this lab, that includes other magnetic fields present, so like a laptop or a phone that might have been a little bit too close. And then visual measuring errors, like there can be small differences when using the meter stick. And then accidentally bumping and touching the phone can affect that. And then the exact location of magnetometer might not be perfect, and that's what we can kind of see here in the diagram. That we might not have gotten that perfect there. And then imperfect calibration for Earth's north and south axis at the beginning of the experiment. So here's our discussion. For the first question, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field, and how would your results have changed? So I said if the meter stick were pointed at an intermediate angle, Earth's magnetic field would interact with the bar's magnetic field, and this would lead to inconsistent measurements, which could change the observed field strength and direction, making it hard to analyze magnet behavior. And then second question was, what if to stick two identical magnets together end to end and run the experiment again. How would you expect your measurements to differ? So the magnetic strength would increase if two identical magnets were stuck together end to end, because it would be the force from both magnets, or the field from both magnets combined, as long as they're aligned end to end. The field orientation, however, would remain the same because the magnets are aligned in the same direction. And that's all. Thank you for listening to my lab 4 presentation.